Section 3.6, L'Hôpital's rule. I know it doesn't look like L'Hôpital, it looks like La Hospital, but it's pronounced L'Hôpital's rule. Very friendly subject we're going to talk about. 5 problems, won't take too long. Let's get started. Alright, let's bring back some old friends. Remember back in the day we learned that sometimes if you plug stuff in, you get 0 over 0. Like in the first problem, if I plug in 2, I get 0 over 0. If I plug in infinity in the second one, I get infinity over infinity. That's no good. You're not allowed to have that. And so what we did way back in the beginning of the year is we tried to find ways to factor things. But there's a shortcut, and it's a whole lot easier. Maybe I should have shown you that way before, but what fun is that? When you get the dreaded 0 over 0 or infinity over infinity, it's called Indeterminate Indeterminate. So here's L'Hôpital's rule. What it's basically saying is you're going to have a fraction and a function on top and a function on the bottom. If you have a limit which requires you to plug something in and you get either 0 over 0 or a type of infinity over a type of infinity, that's no good. This is what you do. You take the derivative of the top and take the derivative of the bottom, and then try plugging it in again. Okay, so if you get 0 over 0 or infinity over infinity, that's no good. Take the derivative of the top, take the derivative of the bottom, and plug it in and see what you get. And if you get infinity over infinity again or 0 over 0 again, you keep plugging it in until you get something that you want. Okay, and what we want is something that's not an indeterminate form. So that's the rule. Let's do a couple examples, not so bad. Alright, example A, we are to find the limit as x approaches negative infinity. 2x squared minus 3x minus 4 over negative 4x cubed plus 5. So the problem with this is if I were to plug in negative infinity right now, I would get negative infinity over negative infinity or negative infinity over positive infinity. Either way, I would have a really big number over a really big number, whether it's positive or negative, doesn't even matter. According to the last slide, it could be any of the infinities over any of the infinities. So we're going to use L'Hôpital's rule. And I'll make that an LHR. So L'Hôpital's rule says, if you have an infinity over infinity of any kind, or a 0 over 0 of any kind, that's no good. What you do is you take the derivative of the top, take the derivative of the bottom, and then plug it in again and see if you have any luck. So if I take the derivative of the top, I get 4x minus 3. If I take the derivative of the bottom, I get negative 12x squared. That's it. So if I were to plug in, infinity or negative infinity in this case, the same problem would occur. I would have negative infinity minus 3, well, negative infinity times 4, which is negative infinity minus 3 is still negative infinity. If I were to plug in negative infinity squared, I'd get a really big infinity, multiply it by negative. It doesn't really matter. I'm going to get infinity over infinity if I plug it in. So some kind of infinity over some kind of infinity. So I have to apply L'Hôpital's rule again. The derivative of 4x minus 3 is 4. The derivative of negative 12x squared is negative 24x. If I plug in negative infinity, that bottom number gets huge, but 4 stays 4. And if you remember, there's a rule that says if you have some kind of number over any of the infinities, it gets to be 0. And that's because if I were to say like 4 over 100, that's point something, 0.02 something. If I were to say 4 over 1,000, that's an even smaller number. And if I were to say 4 over 1,000,000, that's a really, really, really small number. So imagine how small that number would be if it was 4 over infinity. Or in this case, negative, well, actually it would be positive infinity. So I'm now in good shape. Problem A became 0. So that's how that one's done. All right, problem B is the limit as x approaches positive infinity or regular infinity of x cubed minus 4 over negative 2x minus 11. If I were to plug in infinity right now, I get infinity's cubed, which is huge, minus 4, which is still huge. If I were to plug in infinity on the bottom, I'd get negative 2 times infinity, which is negative infinity minus 11, which is still really huge. And what we end up with is something that breaks the rule. So I'm going to apply L'Hopital's rule again. L'Hopital's rule says if you have infinity over infinity, you take the derivative of the top and take the derivative of the bottom and keep doing that until things seem to work out. So if I take the derivative of the top, I get, let me weave that into a better thing, 3x squared, that's it, over negative 2. So if I take the limit as x approaches positive infinity of 3x squared over negative 2, I would get an insanely huge number over negative 2. See, I plug in infinity on the top, I keep negative 2 on the bottom because there's nothing to plug into, and infinity divided by negative 2 is still an insanely big number, but in this case it's a negative number. So the answer we get here is negative infinity. Problem C, limit as x approaches 3 of x squared minus x minus 6 over x minus 3. If I plug in 3 on the bottom, I get, well, let's see what happens. Let's see what happens if I plug in 3. If I plug in 3 on the top, I get 9 minus 3 minus 6, which is 0. If I plug in 3 on the bottom, I get 0, so that ain't good. L'Hopital's rule shall be used. Now, what we learned way, way, way back in the day is maybe you could factor this. And you know what? Maybe we can, but I'm not going to because I know this new rule that might be a little bit more convenient, and maybe that's what I will use instead. L'Hopital rule says if I had 0 over 0 or infinity over infinity, I could take the derivative of the top, take the derivative of the bottom, repeat the process, see what happens. What do I get? I get 2 times 3 minus 1 over 1 equals 6 minus 1 over 1, which is 5. That's not 0 over 0. Look at that. Easy. While we're at it, let's do D. D was sine, well, the limit as x approaches 0 of sine 0 over, well, actually it's sine x, sorry, sine x over x. I'm just getting ahead of myself. I'm so excited. Right now, if I plug it in, I would get sine 0 over 0. Sine 0, according to the graphing calculator or any other method that you use, is going to be 0, and 0 is 0, so that's no good. Let's use L'Hopital's rule. Okay, if I take the derivative of the top, the derivative of sine, is cosine. The derivative of x is 1. If I plug in 0 now, I get cos 0 over 1, because there's nothing to plug in on the bottom. Cos 0 is 1. And last time I checked, 1 over 1 is 1. Hey! Let's save some paper. I have the limit as x approaches infinity of e to the x over x squared. Okay, if I plug in infinity, that would look like e to the infinity over infinity squared. E to the infinity means e times e times e times e. And remember, e is a number, 2.7 something. So if I multiply 2.7 something times itself 1,000 billion gazillion times, I get infinity. If I square infinity, I get infinity. That's no good. L'Hopital's rule. Okay, take the derivative of e to the x, which is e to the x. Take the derivative of x squared, which is 2x, and try it again. If I plug in infinity now, I get e to the infinity, which is infinity as we know from the previous part. 2 times infinity is infinity, so I get infinity over infinity again. Well, that's no good. Let's do it one more time and see what happens. The limit as x approaches infinity, take the derivative of the top, which is still e to the x. Take the derivative of 2x, which is 2. You get e to the infinity over 2, which is infinity over 2, which although looks like it shouldn't be friendly, or it looks like it shouldn't be the answer, is the answer, because infinity divided by 2 is infinity. You're allowed to get infinity, in this case positive infinity. Okay, so there you have it. There you have it.